Hello there. In this video, we're going to start off in what's really kind of the machine learning basics. So I've separated this into about 5 parts. This first part where we're going to tackle really linear regression, logistic regression, how optimization works, and what this whole variance versus bias trade-off actually means. So as with most videos, I'm going to actually use Excel in some of these examples. I have pre-recorded a few Excel videos so that we'll step through kind of how these algorithms and how these different machine learning concepts work. So without further ado, let's go ahead and move into the course. Okay, thank you. Here we are, Machine Learning for Everybody, and this is going to be the Machine Learning Basics, which I'm going to chop into several separate videos. And yes, as with most times, if you haven't seen this before, I say Machine Learning for Everybody, but that doesn't mean that I steer away from the math and steer away from some of the deeper concepts. So I try to get into how these algorithms work underneath the hood, and in order to do that, I do have to show some math. But I try to also show Excel and at times even, just conceptually analogies of how things work. So hopefully you can pick up on however much you can get from this and still kind of understand how these basic concepts work, even if you really don't understand or speak math. Okay, so as I already just mentioned, Control L here for laser pointer, we're going to cover linear regression. Optimization is going to be the second video. We're going to then talk about logistic regression. Variance versus bias trade-off. And then the last video will venture into regularization and what that means. So without further ado, this reflects what I've learned over time. Okay, here's a general syllabus. Control L again. We're going to start with just brief introduction. We're going to dive right in. In fact, some of the last videos really got into more of the introduction sort of part, but today we're going to be talking about machine learning basics. And this is going to set us up to dive right into neural network basics. And you'll see how these different concepts and different algorithms connect to neural networks. And then from there, we're going to get into more advanced neural network architectures, which is really what machine learning and AI algorithms are built on these days. So start with a brief introduction here. Yeah, I mean, if you look up at the header, so much information on machine learning. I mean, you can certainly put machine learning into Google or some other tool, and all these are free books that were out there. MIT and other universities have put a lot of their lectures or free courses online. You can go to Coursera or other massive open course websites, to take these different courses. And of course on YouTube, different websites. I mean, there's really just so much out there, but it's more about kind of curating it and how can you step into this. It's almost at times there's too much, and so you don't know where to start. And certainly that's kind of the place that I was in. So here's my machine learning playbook, or how, again, because I was learning this right at the time, I was taking notes. I was trying to understand, and then I was recounting like what actually happened as I was learning about machine learning. So I wanted to learn it. I didn't know where to start. There's so much out there at the time, and this was maybe 5 or more years ago. There's even more now. I asked a lot of experts in machine learning, where do beginners start? Some recommended sites that weren't that great. Some just said like, oh, you should go back to college and get another bachelor's degree or master's degree in computer science. Most would recommend probably Python and TensorFlow as really a tool that a lot of us are comfortable in using for machine learning algorithms. I did go to websites to try to learn Python independent of machine learning and with machine learning. There's just so many sites. I think that it's almost like a random walk out there of what Google or others put in front of you, and it may not be at the level that you're looking to learn at that time. I did stumble upon scikit-learn. So for those of you that aren't familiar with it, it's kind of interesting to go to and see, even look at like it's hundreds of pages for the manual. And in these hundreds of pages are multiple different machine learning algorithms, and other algorithms about how to train and optimize these different algorithms. So it's a fascinating resource, but maybe not where you want to start when you're trying to learn machine learning. I did ask some non-experts like where they started. A few said Andrew Ng's course on Coursera. He's a professor at Stanford, very famous professor that put a lot of content online on Coursera. The first ones that I took were in MATLAB, which at the time I understood very well. So it was nice to have, a platform that I already understood as I was learning about machine learning. And I continued to take courses. There was a deep learning specialization. It had a series of 5 different courses on machine learning. I learned about Python and coupling that with machine learning. So it's really great. And after emerging from all of those courses, that's really where I had the idea that, okay, maybe I can condense some of the key concepts, throw a lot out in order to make something that I can teach to beginners or people that are just starting their journey into machine learning. It all made sense. The Python codes now make sense. I use them all the time. I started to build that intuition, and I think just getting out there and putting it in front of people and taking in what are probably hundreds or thousands of questions during giving these courses online has really helped me build that intuition about how these algorithms work. Why was it so difficult to learn in the beginning? Maybe I can help. I know that's a lot there, a lot of history of like how my journey was, but I suspect that there's a lot of people out there that are also kind of struggling with where to start and how to begin. So hopefully this course will help in that respect. I did initially, after emerging from this, think, well, geez, I should just write about, a couple of the key topics that people should know about, maybe just a handful and go from there. But really, when I sat down with pencil and paper in front of me and started to jot out all the different concepts that I would tell a beginner and that I think people need to, in order to be fluent in machine learning, they should know a lot of these concepts. It was a lengthy list. And, maybe not all of these are absolutely necessary, but this was my initial list. So this is year 1, month 1, initial list of everything that I was like, okay, these are all really important concepts that people should know about. So this is what I initially then sort of categorized and classified, like how would I structure different courses and content to teach these to the somewhat familiar with machine learning folks. Over time, I have started to get rid and strip away different concepts. And part of that is that I wanted this to stay either a 1-day or 2-day course, and as things evolved over the years within the machine learning domain, and I added things, that became more difficult. And so I really tried to streamline it. So I've gotten rid of some things that are kind of offshoots that I don't think are necessary in order to really get everybody on the same page to learning about neural networks and then learning about these advanced architectures. You don't necessarily need to know about support vector machines, for instance, in order to know about how neural networks work. So that was really how I, kind of streamlined this whole process and this course that I've developed. Okay, now we'll move right into machine learning basics. So yeah, what is supervised machine learning? If we go back to the last part, I'm going to turn on my laser pointer here, but we're going to have a data set, so your machine learning algorithm needs to learn from something or needs to train those model parameters on something. You're going to have inputs, so we're always going to refer to those as X throughout the course. These are going to be features, attributes, different factors within your data set. For supervised machine learning, this is coupled with outputs. So these are outputs or responses, something that you want to predict with your machine learning algorithm. Now, there is a relationship between these inputs and outputs. I mean, it's all structured upon there being some relationship. And there's an actual function. In some cases, it may be a physics-based function, something that actually exists but we don't know about. In others, it may just be patterns and relationships that you're trying to learn between these inputs and outputs. So there's some function there that we don't know. And the machine learning algorithm, again, we're going to refer to things as like f hat. You'll hear me term y as y hat. The hat means approximation. So we're going to try to approximate what the algorithm should be that reflects this relationship. And then what is our prediction of what the output should be? A lot of times when I use this notation, all it's really saying is that the output is a function of this machine learning algorithm, the inputs, and then the model parameters, which we're going to term our thetas. So if we go to something like Python scikit-learn, it really is as easy as there's a model or some machine learning algorithm. You're going to fit it with X, our inputs, and Y, the corresponding output. And then you're going to go ahead and predict for maybe new inputs. So that's where going to Python strips away some of what's actually happening underneath the hood. And so this course is really going to kind of uncover what are these algorithms, how are things actually working underneath the hood, because I think this is too simplistic for really understanding what's going on. These inputs can be a lot of things. So, I think most people gravitate towards thinking of it as a table in Excel, for instance. These can be scalar values, so single values. It could be vectors, so a 1D signal, and you can think of kind of a signal there. Could be 2D or 3D, so images or videos, for instance, tensors, categorical, so categories of things, text and sentences, sequences, time series. So there's a lot of different things that are covered within the inputs. these models. Our machine learning models, this function, can be everything from linear and logistic regression models, which we'll cover here shortly, to random forest, kernel-based models, support vector machines, neural networks. And so we're really going to jump straight from kind of linear and logistic regression straight into neural networks, and then, some of these more advanced neural network architectures. And then the responses are going to be either regression or classification. And I'll talk a little bit about what the difference is, for these different responses. And it really boils down to, is your response variable, is it a quantity for something like regression? Or is it a label, like is it a cat? Is it a dog? That would be classification. And so I wanted to choose an example that hasn't been shown out in the community. So the example that I've been using is one where we have bullets and armor. So we'll have a bullet. There's going to be a lot of different characteristics to this. We're going to sort of restrict the data sets to a few different factors or features. One could be like velocity, for instance, how fast the bullet is going. Gives you an idea of whether or not it's going to go through this armor. It could be the type of armor, like in terms of material is important. The thickness of the armor is certainly important. And then we separated it into these two different types of responses or outputs. So regression or classification. Regression on the left, what you see on this x-axis is thickness. So this is one of our inputs. V50, this is a velocity where 50% of the bullets are going to go through, or correspondingly 50% of the bullets are stopped, right? So you can think about it either way if you're designing weapon systems or designing armor, for instance. And you may want to predict what is this, kind of critical velocity, and so these are really going to be metrics. So the velocity of a bullet, that can scale depending on how thick the armor is, for instance. Classification is a little different. So classification will be, can I predict something like, does the bullet go through or not? And so here I've shown two inputs. So this could be the thickness of the armor and the velocity of the bullet. And you may want to know, does it go through or not? So yeses could be our pluses, no could be our circles. So these are really labels that you're trying to predict. So this label being, does the bullet go through the armor or not? So here's just a few common data sets that are out there. These are all open data sets that if you went out and searched on the internet, you could very easily find, both information about the data set as well as, likely be able to find the entire data sets and download it. So maybe starting in the upper corner, the iris data set, 150 flowers separated into 3 different classes. Life expectancy, so you have a number of lives, and what is the expected life of these individuals given these 20 attributes or inputs. Boston housing data set, 506 houses, and so housing price would be our prediction. Spam base, 4,600 emails, and then you're going to predict, is it spam or is it not spam? Here's a wiki data set, so it's got 460,000 different faces, and it's going to predict both the age and the gender. ImageNet data set, so this has, over 14 million images, probably even more now, and there are 1,000 objects, different classes that it's trying to predict in these images. MNIST has 70,000 images. These are 28 by 28 black and white images, and you're going to try to predict, which of these 10 digits is this image. And then there's a wine quality data set with close to 4,900 images, 12 different attributes of the wine, and you're going to predict a wine quality score. So you can pause at this point, or maybe as I was going through, you're trying to mentally think about which of these are regression, which of these are classification, and I'll unveil on this next slide. Okay, so can the classification data sets please step forward? If you selected this iris one, you are correct. Again, there's 3 different classes of flowers, so that gives a hint of whether it's classification or regression. Spam or no spam. So again, you're predicting whether it is or isn't something. This is a 0 or 1 response, so that would be classification. This one sometimes fools people because it has both. So gender, male or female, this is a class. So certainly this is a prediction. Age is something that, again, it's a value or a quantity, and so that would be a regression task. And the way you might want to think about that is, well, we could predict these as separate classes, but there's a relationship between these different, classes, so to speak, or quantities. That the 88 years old always comes after 87, which comes after 86. Whereas in classes, there's no relationship or ordered relationship in that manner, or often there isn't. ImageNet, these 1,000 objects are 1,000 different classes, as are these 10 digits. Can be viewed as these 10 different classes. So even there's an ordered, 0 through 9 has an order. With respect to the inputs, it just doesn't make sense in this scenario to have a response like 1.1. What does that mean? Okay. Are we ready to talk about neural networks yet? No. Sorry, we just started, Han. I mean, what do you want me to do? So there we go. Okay, I usually give like a true-false test. So from time to time, I'm going to throw some things up on the screen. Some of these true-false statements, just for people to kind of understand where some people have tripped up on these true-false questions. So let's start with the top one. Mean squared error, or the L2 loss function, is commonly used for classification problems. And that is false. We'll talk a little bit about loss functions. Actually, the mean squared error, or the L2 loss function, is commonly used for regression problems. And then classification has a different kind of loss function that's often used for it. The mmult function in Excel is associated with linear regression. This is true. So we've kind of shown this multiple times, how a matrix multiplication of your inputs, your x's, times theta, your model parameters, really gives you a linear regression response. And so we'll get into that in this section. So here we go. Linear regression, the basics, up above here. Here's your basic, very basic linear regression equation. So again, you have the output y is equal to m, or, we're going to convert this into theta, times x. So where m is kind of this slope term. If you remember back to the days when you may have talked about this in school, m will be the slope, rise over run, if you will, whereas b is going to be the intercept. So this is going to be like where it hits the y-axis when x is 0. So these are your two. This is your basic linear regression equation. And so if you look at these two independent of each other, so first let's set b equal to 0, and let's just choose different values of m, or the slope term that acts on our input. So if you use 2, 1, 0.5, this is going to modify, again, the slope of this line. Where 0.5 is going to mean that changes in x don't modify y as much, whereas a high value means that a small change in x is going to have a large effect on your output. So it's really kind of how sensitive your output is to your input. This is setting x equal to 1, so you see kind of this 45-degree line, and changing the value of b from 0 to 1 to 2. You can see how it shifts. So it doesn't change the slope at all, but it actually shifts the line up and down. And again, I think this is actually showing 2 and plus 4, because that's where it's intersecting x equals 0. But this is showing kind of that change to the function, with that intercept term. Okay, so we're going to take this and, single linear regression, you're going to have y is equal, we're going to call this theta, and we're going to use these theta terms, from now on. So rather than have multiple different terms, and you'll see how this makes it easier to talk about these different model parameters. So we're going to kind of reorient this whole thing, where theta naught, this intercept, is first, or theta 0, if you will, plus theta 1 times x. So this is a slope term acting on your input. And here's some data where we have, again, armor thickness versus the velocity, where 50% of the bullets go through, and I just drew some lines on here to give you an idea that at some point we're going to have to figure out, like, how do you choose the best line? But for now, just know that we have this real data, these data points, and we're trying to fit a model that captures this relationship between the armor thickness and the V50, this quantity that describes how effective a bullet is or how effective armor is. Yes, and once again, there is the slope term. And, the intercept term is going to be where it intersects this y-axis when x is 0. So that's single linear regression. But almost all the time, you're going to have way more, features and inputs than just one. And so in these cases, it's called multiple linear regression. And what you have is, theta naught, and you're going to have theta 1, which is going to act on one of these features, say x1. Theta 2 will act on x2. So you're going to have this kind of slope term that acts or multiplies by the input up to the number of features that you have in your input. And I usually show this just for the people that are curious about the math and how this works. Like, can you solve for these parameters, like, right off the bat? And it turns out you can when the data sets are very simple. And it very quickly gets much more complex as we go along, and I'll talk to that later. But what you have is your output is equal to the input matrix multiplied by the theta matrix. So in this case, you have your x's, you have your thetas. In most cases, you're going to have multiple different runs. So each of these is going to be a different row, and each of these different rows is going to have a corresponding output. And you can do the linear algebra to actually solve for the theta parameters like right off the bat. And how you do that is you have to multiply by an x transpose. This makes the matrix square. Once you have a square matrix, you can multiply it, or you can take the inverse of that, multiply it by x transpose, and multiply it by y. So you had to do all of these steps in order to isolate what is the model parameters. So for those of you that are curious about this, that's how this looks. But we won't use that as often as one might think, and I'll go into that in the optimization section. So yeah, how do you choose between these different model parameters, right? Who's to say which of those different lines that I drew in is the best line at capturing the data? So here I've actually constructed a plot where I'm going to try to explain like how you can tell which of these functions is actually the best function. So with this plot, these red dots are actual data. So these are the actual outputs that were measured somehow. These blue ones are our predicted outputs. So again, they're for the same thickness. We're gonna make a prediction based on this model, or this linear regression algorithm. This linear regression algorithm is going to have different theta parameters. So you've got theta naught is this 391, theta 1, 6.72. Again, this is a slope that acts on the thickness, and this is the intercept term. And then when we talk about loss functions, like what actually is a loss function? For each of these pairs of like the actual response and then the predicted response by the model, what we want is we want to have some value or quantity that tells us how good the prediction is. So one way is just to take the difference between the two. Now, this is going to give a positive value in some cases and a negative value in other cases. And so if you square that, that's going to eliminate these negative values. So now everything is positive. And obviously, if that line length is 0, then that means your predicted response is the same as your actual response. So that's a good thing. But if it's very large, obviously if it's a long line, when you square that, it's even larger. So that's how this loss function works. Again, if you look kind of down below, it computes the error between the actual and predicted outputs for an individual observation. So you're going to do that for every different data point that you have in your training set. And then when we talk about the cost function, and again, here's a term that you've probably seen used or may have seen used. Mean square error is another name for this L2 loss function. And what the cost function is 1 over the number of observations, and you're going to take all of these loss functions and you're going to sum them up. So this is an average of the loss functions that you have. And now you have one value, a cost function, that can be used to actually measure how good is your model. So now if we go back over here, mean squared error 317, that's a metric that describes how good this particular model is. Now when I say L2 error, There's an L1 error, there's an L3 error, there's multiple different variants of this. These are the two common ones. The most common and the default for regression problems is going to be the L2 error or L2 loss function. When you look at the L1, this corresponds to the mean absolute error. So again, it's a similar sort of quantity. What you're doing is you're taking the difference between, again, actual and prediction. And in order to counter that you have some positives and negatives, you just take the absolute value. So that turns all the negative values into a positive. And now you can use the same sort of methodology to obtain the average of those and obtain a cost function. In some cases, you might want to select different loss functions, for different purposes. So this one will be likely more robust to outliers. So if you have some outliers here, again, with an L2, you're going to square them. So if you have something very large and you square it, it may shift your whole model in order to capture that. In order to minimize that line length. Whereas because the L1 error isn't squaring that term, it's not going to, shift your whole model as much as something like the L2 loss function. Again, that just happens like if you do have outliers in your data set. So that's where a lot of people, though, will default to the L2 loss function when they're constructing their regression machine learning algorithm. And so, how can you tell the difference between, different algorithms with different model parameters? Well, here we've just shifted theta naught from this 391 value down to 380. So we've shifted this down. I mean, you can visually see that, a lot of these lines got much larger, or longer, which indicates that, again, the predicted values are far away from what the actual values are. Because these are large values now and you're squaring them, your mean squared error actually shows as higher. So you see that's 442 over here versus 317. That would lead you to believe that the one on the left is a better model for capturing this, the actual outputs than the model on the right. So we now have this parameter, this cost function, mean squared error that, can tell us like which of these algorithms with different model parameters is better at capturing this data. And here's just like, what if you change the model parameters systematically? So the plot that I did show on the left was actually the optimal model parameters. So you see here 391. I believe this is our theta naught term. 6.72 was our theta 1 term. If we start to shift it, how does that mean squared error term, what does it look like? So if you just change theta naught, it's parabolic, so here's the parabolic shift, here's theta 1. If we change that, it's another parabolic curve. So, as you get further and further away from 6.72 and 391, the cost function is going to increase. And there's the blue value of kind of what we showed, we showed this 380 value on the last plot. And so really it comes down to, again, we have our output, our predicted output, which is, a function of this linear regression model with these model parameters and our inputs. And we want to minimize this cost function by changing these theta or these model parameters. And that's going to give us this optimal model. So really the question is, if we start somewhere, let's say we start at the blue star, how do we get all the way down? How do we know when we hit the best model? And that's where optimization is going to come in. We're going to talk about that in the next part of this video. So here, if only there was an automated method to obtain this, because most times you aren't going to have just one input. You're going to have multiple inputs. And so, having some sort of methodology that's going to automate this whole process in finding the right model parameters is really important and really helpful. So with that, I'm going to shift back to the next video. What you've learned here is really linear regression. So you can have single linear regression, which has one input, or multiple linear regression, which is when you have multiple different inputs. We talked about classification and regression. So you want to know kind of what is a class or classification, when is it regression, because that's important in selecting your loss functions. And we talked a lot about loss functions as it pertains to regression. So these loss functions are things like, the L2 loss function. The cost function for that is the mean squared error. We even talked a little bit about the L1 error. So in the next video, we're going to talk about optimization and how can we automate this whole process of selecting all of these different model parameters.